Right. Sequential considered harmful, or when things just don't add up. So what we're going to do is we're going to do a little experiment by adding 10 billion 0 to 1 numbers using the standard mechanisms in the language. So the for loop, accumulate, and reduce. We're going to see possibly what happens when we jiggle the inputs around as well by permuting it. So here's the first go. That's brilliant. Look, they all agree. A for loop, accumulate, reduce. They all give the same answer. Fantastic. 3 flight computers are agreeing. But when we look at the disassembly, they're actually all doing the same thing. They're doing a scalar double addition on the XMM register. So it's just one function, same function being called. So now we permute randomly. Oh no, we've got a different answer. Let's permute again. We might get back to the same answer. Alas, not. We're just getting different answers. Wonder what the worst thing is that can happen. Ariana Bang, not Ariana Grande. Blew up in 1996. Right, let's consider some equivalent calculations. A large number, subtracting that same large number, and adding a small number. We've got 3 expressions here. And only the middle one, where we're adding a large number and subtracting a large number and adding the small number last, is going to give a sensible answer. So starting off with the same large number, A, adding a small number, B. When we add these things together, the true value is about 25 digits. With standard C++ environment double, well, that's only about 16 digits. So we're going to get something a bit like this. But the actual result is T. So we can write this in a little equation. A plus B plus an error is equal to T. And we can, well, let's rearrange that. So we've got the error now, an expression for the error, and we can actually do some error correction. Now we can put this in a lambda, which is the summation, and we can call it the Kahan lambda. What we're going to do is we're going to, as well as actually adding the numbers together, we're going to have a rolling error correction. We'll store that inside the lambda, or the lambda initializer. So the lambdas are mutable. And what we can do is we can just pop this, the end of your accumulate or your reduce call, and you'll get the error correction. That's not the end of the talk. Add same size numbers if you want to retain accuracy. You can see that that was a problem before. But there's another one we can do, is if we're adding sets of numbers, if we add sets of the same size, well, they're probably going to have the same size number as well. So we should add sets of the same size for accuracy. Now, the thought experiment is we add 100 numbers together by performing 99 plus operations. But what we want to do is we want to engineer it so that the last operation has the largest error. The best way to do that, well, we add all the numbers together in one and add the final element in the last one. So we can also do a really bad error thing with a preceding sum, and we can do this recursively. So this is actually, unfortunately, quite familiar because this is what we've just been doing, creating the largest error at each stage of the addition. Now, that could mean sequential summation is considered harmful. Let's try and do it a different way. We're going to try and minimize the error. And what we could do here is basically add sets of the same size. Our last plus operation is adding 2 sets of the same size. And to get those sums, well, basically, we decompose and decompose and decompose until we just get pairs of doubles at the bottom that we're adding. This is pairwise summation. Let's do the experiment again. The last 2, Carl summation pairwise, are also done using SIMD instructions. And what we see is these last 4 bits on the slide here are all given the same answer. And when we perturb, we get the same answer again and again. And we got a slight push from the last one there. But basically, we're getting the right answer. So why we got the wrong number was because we're adding them up in the most inaccurate way possible, not because of rounding errors or anything like that. We just did it the wrong way. We can use a SIMD implementation of this. As we recursively decompose the addition, at the bottom level, we can just have SIMD instructions and extract the scalar with this kind of scheme here. Is it fast? Yeah, it's very fast. The SIMD pairwise implementation rocks up at about 3.5 billion a second, whereas at the bottom level, the blue STL is rocking up at about 800,000. And even with the Cahan expression, it's great. We're still going faster, but we're actually getting the answers right. So how bad is accumulate? Efficiently, it's about 12% efficient. Accurately, well, it's not good. Oh, and don't forget the booby trap. It would be nice if we could have a new algorithm, please. So pairwise reduce, pairwise transform reduce, and there are resources available here. That's me done. Thank you very much.